All right, so welcome to lecture number 6. This is our Math 211, and we're on September 16th, and we're continuing on chapter 4. So I'm going to share my screen here, and then let's load up chapter 4. To recap what we've done previously, we did, at least in words, we did the addition rule, where you basically, you count the number in one category, you count the number in the other category, and you add them. You just have to be careful about whether or not you get repeats. I don't think we spoke specifically about that yet. So the first examples that we've done, we didn't just do one calculation and then the other and then added them, but rather we combined it all together and mathematically gave one answer. And we talked about disjoint events when they have nothing in common, where you can just do them separately and put it all together at the end. And we did that. We did no, we didn't do this.
No, we're on page 4.
So we're on page 4. Okay.
Yeah, at the bottom. Like, I believe complete this rule of two events A and B.
Okay. Beautiful. Okay. So we did this already, but let's recap. Which of these two Venn diagrams represents disjoint events? The first or the second? There's two Venn diagrams there, huh?
The second one?
The second one, if A and B are disjoint, they have nothing in common, which means there's no overlap, because the overlap is what they have in common, and they don't have any in common. So, okay, if two events A and B are disjoint, then what is the probability of A and B? If they are disjoint, they have nothing in common, then what is the probability that both of them can occur simultaneously?
0.
0. It's impossible for both of them to occur simultaneously if they are disjoint events. It's not mathematically possible. But if they are disjoint, then what is the probability that one or the other occurs? Is it
Oh, sorry.
Well, I can't give a number because I'm talking about a generic situation. I mean, it could be picking a number from 1 to 1,000,000, and A being getting 17 and B being getting 2 to 6. Right? We're talking about any event. I'm not looking for a number here. I'm looking for a formula. If you want to find the probability of A or B when A and B have nothing in common, can I simplify that formula and come up with a way of getting it that would always work no matter the situation? Can anyone think of something that might work? So what I can do is I can calculate the probability of just A by itself, ignoring B. I can calculate the probability of just B by itself, ignoring A, and then do what with those two numbers?
Would you divide?
Not divide.
Multiply?
Not multiply.
Add.
Hey, there you go. Add. The number of ways of getting A plus the number of ways of getting B gives the total number of ways of getting A or B. Correct? So the likelihood of A plus the likelihood of B is the likelihood of A or B. But this formula is only valid when they have nothing in common. As we're going to see very shortly, it does not hold otherwise. Does that make sense? Yes, no, maybe so?
Yes.
Okay. So the circles in this Venn diagram show the proportion of students in a large class who got at least 8 hours of sleep last night. That's the S circle. And the proportion who exercised at least 30 minutes yesterday, that is the E circle. Of course, you also have these guys. And what does this 18% signify?
But the outside universe?
Well, the universe is the whole rectangle, including all of this, right? This whole rectangle is the universe. So I'm looking at just this part. Who would be characterized? That 18% is referring to which people would fall into this category here?
People who didn't do either.
People who did not do either. They did not exercise 30 minutes, so they're not in the E circle, and they did not get at least 8 hours of sleep, so they're not in the S circle. There's 18% of the people fall in that category. And what about these guys right here?
They did both.
They did both. Okay, so let's see what the questions we have here. It says, you pick a student at random from this class, find each probability below. What is the likelihood? What is the probability that someone, let's do the easy ones first. Let's do this bottom one, the bottom left. The probability of S and E. How likely is it that someone that we picked was in both S and was also in E?
0.22.
0.22. There's 22% chance that the random person that we pick falls in that overlap. That's the easiest one, I think. Now let's do P of S. What is the likelihood that somebody falls in the S circle?
15%.
That is not correct. 15% is only part of the S circle.
Oh, plus the 22.
So what should P of S be?
27, 37.
0.37. There's a 37% chance that we pick someone in S, because remember, if I'm asking about S, I don't care about E. I can just delete this circle mentally. All I care about is S. And these people here, they might have been an E, but they're an S, and that's what I care about. So S is both of these. Do we agree?
Yep.
Yeah.
Okay. What is the probability that somebody was in circle E?
67%.
Do we agree with that?
Yes.
Okay. How about the probability that someone was not in S?
Would it be 0.07 where you just subtract?
0.07?
Would it be 0.63?
Oh, okay.
So it is 0.63. Can you explain why?
Because you add the 45, which is on E, and the 18, which is on the bottom, which gives you 0.62.
Not S, not S, S, S. So not S would be 0.63. Do we agree?
Yes.
What about not E?
Would it be, oh, sorry.
0.18 and 0.15.
Well, what is that?
0.33.
0.33. By the way, what do you notice about these two and these two?
They add up to 100.
They add it to 100% because either you're an S or you're not an S. Either you're an E or you're not an E. So as pairs, they have to add to 100%. Agree?
Yep.
Now, what is the probability that you're not an S and you're also not an E?
0.18.
Excellent. The only people that are not an S and are also not an E are the ones who are neither. We agree?
Yes.
Okay, so now let's do the tougher ones. S or E. What is the probability that you are an S or E?
Would you add the 0.15, 0.22, and then 0.45 all together, which I think it gives you 0.82?
0.82 is correct. S or E, that's an S or E. That's an S or E. That's an S or E. That's not an S or E. So we add up those three circles. Yes? Yes? No? Are people getting this?
Yes.
I know the vocal few are getting it, but I don't know about the unvocal majority. Is anyone not following along here?
So basically we just calculate whether, like, for example, it says not S, so we just what am I thinking?
I don't know.
So basically we either subtract or add depending when it's asking, or like just pick.
Well, you would never subtract. What do you mean by subtract? I mean, there could be manipulations that end up with subtraction, but in this case, you're looking for all of the numbers that satisfy the criteria that you're working with, and then you add them all together.
Oh, okay.
Okay, so in this last one, not S or not E means that I am happy if I'm not an S, and I'm happy if I'm not an E. I don't need both, I just need one. Would I be happy with these guys? The 0.15? Happy or unhappy?
Unhappy.
Why am I happy?
If you're asking if you're in not S and not E?
No, not S or not E. Not S or not E. Do these guys make me happy if I'm looking for someone not an S or not an E?
Oh, they make you happy.
Why do they make me happy?
Because you're asking either or both.
So which one is satisfied?
Three in the middle.
No. I'm saying for this one. Why?
Oh, yeah.
What makes me happy about this? Is it not S? Is it not E?
Not E.
This
It's
one's
not.
not E. What about this one? Am I happy?
No.
No. Am I happy here?
Yeah.
Why?
Because it's not S.
But it's not S. Am I happy here?
Yes.
Why?
But it's not neither.
It's neither. Once I have one, I'm happy with the other. So these three numbers would then be not S or not E, which gives me what?
0.78.
0.78. Does that make sense?
Yes.
Okay.
Yes.
By the way, what do you notice? I just deleted everything. I'm not sure if I can undo it. Okay, I can. So what do you notice about, how do I, oh, okay, 1 second. What do you notice about these ones? The probability of S, the probability of E, and the probability of S or E. Do these two add up to this one?
No.
But wasn't that what the formula what we had here was? If I have A or B, I can do them separately and add them. Why is that not working here? Where if I have S or E, I can do them separately and add them. Why do I not get the right answer?
Is it because they're overlapping? They're not disjointed?
Exactly. It only works if they are disjoints. Do not try to use that rule. We'll come up with a different rule in a second, but do not try to use that rule if they are not disjoints. Hopefully that makes sense and you don't make that mistake. So here is in boxed form what we came up with earlier. If A and B are disjoint, then the probability of A or B equals the probability of A plus the probability of B. You do them separately, you add it together, and you have your final answer. Okay? So, for example, if you roll 2 dice, find the probability that you get a sum of 7 or you get doubles. Well, the first thing you want to ask yourself is, are these disjoint events? Can I get both at the same time?
No.
No, if I cannot get both at the same time, then they are disjoints. So to find the probability of a sum of 7 or getting doubles, and I'm just going to use a shorthand, I'm going to say 7 or D. Although if you go out there in the world and you say, hey, 7 or D, they're not going to know what you're talking about. So it only makes sense in the context of this problem. I can do it as the probability of getting a 7 plus the probability of getting doubles. Now, what is the probability of getting a 7? How likely is it if I roll 2 dice that I get a 7?
3, would it be out of 12?
Well, how many outcomes are there when you roll 2 dice? How many equally likely outcomes are there when you roll 2 dice?
36.
36. Of those 36 outcomes, how many give you a 7?
I don't know if it would
Is
be
it
3
3?
or 6.
3, I think.
Okay, well, tell me which 3, and then we'll see if we can find others. Which 3 do you suggest give me a 7?
There's 4 and 3, 2
4
and
3,
5,
2
1
and
and
5,
6.
1 and 6. Anything else?
Um,
And then can you do 6 and 1?
6 and 1,
And then 5 and 2? And
5
then
and
3 and 4.
2, and
Yeah.
then what?
3 and 4.
3 and 4. Because remember, first die, second die is
Second die.
different, second die, first die. So 6 ways of getting a 7. So 6 over 36. How many ways are there of getting doubles?
$12.
What are the 12?
1 1 2
1
2
1 2 2
3 3
3 3
4 4
4 4
5 5
5 5
6 6
6 6.
and then 1 1 2 2 3
They
3.
have 1 1.
But the dice, no?
Well,
One die and the other die?
First die, second die. If I get 1 1, I mean each one was a 1.
So then the opposite die, or I guess the opposite die would still be the same number. Never mind. Sorry.
So what should it be?
6.
6. So 6 over 36 plus 6 over 36 gives me?
Whoa, wait. Sorry. For the 1 6 and then the 2 5 and the 4 3, can't you just like, all right, so I wish I could like write on your screen.
Me too.
So 1 and 6, there's one die and then the other die, right?
Very well. First die, second die.
Okay, first die, second
agree.
die.
First number is first die, second number is second die.
Okay, never mind. Okay,
We
never mind.
can write on the screen, by the way.
Oh, really?
Left a little blue mark there just just to see.
Oh, that just opened up Pandora's box.
If you hit view
Remember,
option,
I'm recording this, so let's not get me fired by putting anything here that can get me in trouble. Okay.
we don't just checking if it worked.
But yeah, so if you want to if you want to write something down, that's fine. Within reason.
Well, it's kind of like, I was just gonna say, like, what if the second batch of numbers represented like the second die and the first die, which would be the same as like the first batch of numbers?
Well, whatever your convention is for the problem, you can't switch it halfway through. So if
yeah. So you have to stick like 1 and 2 and 1 and 2.
Exactly.
Yeah. Okay.
Okay, so what is 6 over 36 plus 6 over 36?
12 over 36.
Which reduces to
1/3.
1/3. So the probability of rolling a 7 or doubles would be 1 in 3. I don't know any games out there where 7 or doubles is a winning roll, but there are new games being invented all the time. So maybe you can make one. Who knows?
There's a game where 7, 11, and doubles are winning numbers.
You talking about craps?
No, it's like a drinking game.
Oh, well, if it's a drinking game, everyone's a winner. All right. Anyways, are there any questions on this page? No. Okay. Moving down. If you pick a card from a standard deck of 52 cards, what is the probability that you get an ace or a jack? First, ace and jack, are those disjoint events? Can you get both an ace and a jack simultaneously when you pick one card?
No.
No, it's impossible, right?
Yes.
Okay. Therefore, they're disjoint. So the probability of an ace or a jack is the probability of an ace plus the probability of getting a jack. And what is the probability of getting an ace?
4 out of 52.
4 out of 52. And how about getting a jack?
4 out of 52.
For a total of?
8 out of 52.
Which reduces to? Let's see your elite arithmetic skills. What does that reduce to?
4 out of 26, 2 out of 13.
2 out of 13. Do we agree?
Yep.
I hope so. I hope so. All right. What about if they're not disjoints? So a bowl contains 4 green M&Ms, 6 red M&Ms, 7 blue M&Ms, 3 green Skittles, and 5 red Skittles. You select one candy at random. What is the probability that it is green or an M&M? So, what is the right answer to this question? Oh, that's funny. What is the right answer to this question? All right, well, let's start there. What is the right answer to this question?
$13 out of 20.
Try again. I think try again.
Would you have to add all of them together?
4 over 25.
Try again. Would you have to add them all? I don't know. I'm asking. What's the probability of getting a green or a red? That's the question.
Oh, I thought it was only green. Sorry.
I don't mean green or red. Green or an M&M.
100%.
You are guaranteed to get a green or an M&M.
Oh my God. I thought they were all
20 out of 25. Yeah, I missed the blue M&Ms. I didn't see the blue.
So what is it again?
20 out of 25? Because you can get 4 green, 6 red, that's 10, 7 blue, that's 17, and then 3 green, which is 20.
Okay. So green or M&M. I'm happy because it's green and an M&M. I'm happy, M&M. I'm happy, M&M. I'm happy, green. I am unhappy, not green or an M&M. It's 20 out of the 25 total candies that I have in front of me. Do we agree?
Yes.
Okay. Now, does the addition rule for disjoint events give the correct answer? Well, let's compute that. What's the probability of getting a green here?
$20.
Just 20? Just 20? That's a pretty big probability.
4 out of 20.
4 out of what?
Oh, wait. 20. You asked just for green, right? Or did you ask for M&M or a Skittle?
Just for green. Probability of green.
7.
A 7?
7 out of 25?
7 out of 25. There's still 25 candies, of which 7 of them are green. Probability of getting an M&M.
17 out of 25.
17 M&Ms out of 25. And if we add these, like the rule for disjoint events, what do we get?
24 out of 25.
24. Was that the answer that we got in part A?
No.
No, in part A, we got 20 over 25, and now they're saying it's 24 out of 25. One of these must be wrong, but this is the right answer to the question. So this has got to be correct, which means the addition rule for disjoint events does not apply here. Why not? Because they're not disjoint. Can you get both a green and an M&M simultaneously?
Yes.
Then they're not disjoint. Because they're not disjoint, we have to have a more sophisticated rule. How would you modify the addition rule for disjoint events so that it works for situations like this?
You can use the diagram, the ones that are joined together. I think.
Which ones? Which diagrams?
The ones that like they're not disjointed, they come together.
I mean the Venn diagrams.
Yeah, the Venn diagram.
Yeah. 100%. We can always use Venn diagrams, but we want to have a formula when possible, especially when problems get so complicated that Venn diagrams no longer become really a feasible way of approaching them. We'd like to have a formula. The addition rule is a formula. P of A or B equals P of A plus P of B, right? That's the addition rule for disjoint events, correct? P of A or B mathematically is the same thing as P of A plus P of B. That did not work here. So the question is, can I modify this formula so that it does work? Can I change? Oh, someone chatted something. What they say? They said, is it the one on the next page? Well, let's take a look. Well, yes, it is. Okay. But let's now look at the next page and let's try to understand why it makes sense that that should be the modification without looking. So when we did it directly, when we did it just by counting, and we know we get the right answer, we ended up with 20 out of 25. And when we did it the wrong way by doing them separately and putting it together, we ended up with 24 out of 25, which is too much, which means we got to take away something. We got to take away something to get back to the smaller correct answer. In this case, what were we taking away in our example? What
those that are both green and M&Ms?
Those that are both green and M&Ms. There's 4 of them. Right? To get back from 24 to 20, we got to take away the 4. Why those 4? And the answer is because we counted them twice. We counted them because they were green, and we counted them because they were M&Ms. So we counted them twice. Anything we count twice, we have to remove. How do I describe the ones that fall in both A and also in B, so I know what to remove? How do I mathematically describe the overlap of A and B?
Oh, so you subtracted they subtracted the 4 green M&Ms since it was repeated, correct?
Correct. So how do I describe generically for a generic A-B situation? You have A is one set, B is another, A, P of A plus P of B minus P of something. How do I describe the guys that fall in both A and also fall in B?
Do you just put P, A, B or something?
Well, what's our notation for the overlap of A and B? No, there are actually books that do that, by the way. They use just A, B for the overlap and they don't put a symbol inside.
Okay, would be, you just use C?
No.
I'm probably wrong. Yeah, I know. I'm probably wrong. I'm just trying to see. But
so we use, actually, one second. Do we even use it here? No, they don't do it here. So ignore that symbol. You haven't ignore that symbol. We are going to use and P of A and B. So put that in there. Okay, so for us, P of A or B is equal to P of A plus P of B minus the stuff that's in common. What's the stuff that's in common? The stuff that's in A and B.
Professor,
Yeah.
I can't see what you're writing, what you wrote, because you wrote it a little bit differently than what we actually have. I'm not able to see it. Can you? Oh, okay. It's not a move with it. Okay, I'll just try to see right now because you put ends. You wrote it a bit different. Maybe when you're recording, it'll show. So I'll just go look back at the recording.
What did I do differently? Because I wrote P of A and B.
Oh, okay then. Oh, then we're good. It's fine.
Okay.
Thank you.
I just had no room, so I kind of made an arrow to say put and here.
Oh, okay, perfect. Thank you.
Professor, so if we were to use the thing we just did right now, this thing, would it go like P, the probability of M&Ms or green equal probability of M&Ms plus probability of green minus probability of M&Ms and green?
Yes, that's exactly it.
Okay.
That's exactly it. So let's use this in the following example. Compute the probability that you get a sum of 10 or doubles. Now, is it possible to get both a sum of 10 and doubles?
Yes.
Yes, so there's overlap. They are not disjoints. So we want the probability of what I'm calling A or B. Now, according to our rule, it's the probability of just getting A plus the probability of just getting B minus the probability of A and B. In our example, what is the probability of rolling A? What is the probability of rolling A?
3 over 36.
3 over 36. There's 3 ways of getting a 10, 4, 6, 5, 5, 6, 4.
Wait, so then now you wouldn't do 5, 5, 6, 4. What was the other one?
5, 5, 6, 4, 4, 6.
Oh, yeah. Okay, yeah, never mind. Sorry. There we go.
Okay. What is the probability of rolling doubles?
5, 5, so it's just 1 over 36, correct?
No. Not doubles and 10. Just doubles. B by itself is just doubles.
6 over 36.
6 out of 36.
Oh, okay.
Right now, subtract both sum of 10 and doubles. What's the likelihood of that happening? How likely is it that I get a doubles and I get a 10?
1 out of 36.
That's 1 out of 36. For a total answer of
8 out of 36.
8 out of 36. Which reduces to what? What
2
does
over 9.
2 over 9. So does the addition rule work even when the events are disjoint? The answer is yes, but you just can't use the disjoint version. You have to use the general version. Does that make sense?
Yes.
Yes.
Yeah.
Yes, I can't. Yeah. I'm not even going to write it. I'll just set it. Yes, if you use the general rule. Okay. Any questions before we go on? Everything making sense so far?
Yes.
Okay. I am recording, by the way. I hope I'm recording. I don't see a...
You are.
Okay, good. Okay. Example. You will be assigned to observe a student chosen at random from a third grade classroom. In this classroom, 80% of the children are English learners, E, or receive free/reduced price meals, M. 40% are English learners and receive 50%, and 40% are English learners and 50% receive free reduced price meals. Compute the probability that the child selected is both an English learner and receives free reduced price meals. And let's also illustrate the situation using a Venn diagram. Oh, and that's the end of the section. Yay. How nice. So, someone walk me through this.
So they already have the 80%, which the probability is M or E. And then they have the probability of M, which is 40. You just do that one equation thing, the long.
So let's list it. So tell me what to write. Give me the 3 pieces of information in mathematical form.
Probability.
Sorry, I have a question. The general rule. So there's only the general rule and the disjoint rule, right?
Those are the only 2 rules we have.
Oh, okay, perfect.
And the general rule, by the way, will hold even in the disjoint case. It's the most general rule. It'll hold all the time.
But there's no
there's no third version.
There's no, yeah, right. It's just general and disjoint.
That's it. General is always works. Disjoint only works when they're disjoint. But the general.
For this, it would be the general rule.
Well, if there's an overlap, is there an overlap?
Yeah, because they want the probability that is an English learner and the free reduced.
Yeah, but then maybe it ends up being 0. Maybe there's no overlap. I don't know. We got to do the math to see.
Oh, but I'm saying you would use the general rule though to figure it out.
I would use the general rule until I know otherwise.
Right.
Okay, so mathematically, what do I know?
M or E.
Probability of M or E is what?
80%.
80%, right? The very first thing they say is that 80% are either English learners or receive free/reduced price meals, M or E, 0.8. What else do I know?
%40 are English learners.
So how do I write that mathematically?
Let me see. Okay, so P probability E equals 0.4.
Okay, probability of E is equal to 0.4.
And the probability of M is 0.5.
Probability of M. Wait a second.
Right?
Hold on. Can I?
You can also create circles for the Venn diagram.
Crazy. Why didn't anyone say? Oh crap! Why didn't anyone say anything like before I? You guys just wanted to see me suffer. I know.
I thought about last class about telling you that about typing, but I didn't want to be rude.
No, this is seriously a game changer.
And I bet if you type, it'll move along with the pages.
No.
Oh no.
I think you can select it though with the mouse. Let me see. Can I just?
Can I?
Yeah, if you hit the mouse tool, are you able to?
So like select like this. No.
There you go. But it has to be in a single text box. Or else you're going to be moving each piece individually.
Right. Okay. So a new text box. So now what do we want? Compute the probability that the child is selected is both an English learner and receives free reduced price meals. What would I write mathematically? What am I looking for here?
Probability M and E.
P, M, and E. So equals, and right now we have a question mark, right? This is what we're looking for. This is crazy. Of course, now I have to make sure they line up. Okay. So do I have a formula that connects these four quantities?
Yes.
Yes. It says P of M or E is equal to what?
80%.
Well, this what's the formula? P of M or E equals?
Oh, equals probability of M plus probability of E minus probability of M and E.
M and E, you mean, right?
Yeah.
Okay. Now, do I know what these things are equal to?
Yes.
Okay, so let's solve for P of M and E. Can I do that? Go ahead, please, and do that.
Would it be 80 equals 40% plus 50% minus probability of M and E?
So 0.8 equals 0.5 plus 0.4 plus or minus, we'll just call it X. Because actually I just write it out. Plus probability of M and E. Right? Yes?
Yes.
So,
yes.
and therefore, what is the probability of M or E and E?
10%.
10%. We agree?
Yep.
Therefore, probability of M and E equals 0.1. Okay.
I have a question, Professor.
Yes.
For the formula, I thought it would be 0.8 equals X plus, oh wait, sorry. So we're trying to find P, the probability of M and E.
Yes, right. Compute the probability, right? Let's look what they're looking for here. Compute the probability that the child selected is both an English learner and receives free reduced price meals. I want to be in both E and M.
So for probability of B, what is that? What does your B stand for? I thought the B stood for both. That's why I was confused.
No, A and B are just arbitrary objects. X and Y, A and B,
Yeah.
Ralph.
But like for the sake of there's so many M's and E's.
Well, no. E, they told me in the beginning, E is English learners.
Right.
M is free price meals. There's no E.
I think he's talking about the probability. It looks kind of like a, I think it's supposed to be an E.
Oh, is it an E?
Oh,
It's
this guy?
Yeah.
Well, if only I had known about this in advance.
Oh, okay. Yeah. I was like,
it's the probability of E equals 0.4.
Are you saying my handwriting is not neat? Is that what you're saying?
Mine is no better. I was just making sure.
Hold on, wait. Mine is no better than you're saying it's not neat.
No, I mean mine is sloppy.
That's what I mean. The class.
Yours is neat. Mine is sloppy.
Oh, okay, fine. Okay.
Okay.
So hopefully that answers your question.
Yeah, it did. Thank you.
So now let's make a Venn diagram. There's got to be a way to make straight lines here. Okay, let's see if we can figure it out. Draw. Yeah. Oh yeah, that's what I'm talking about.
So in other words, we're just looking for that little spot in the Venn diagram where they both come together, right?
Yes.
Okay.
You can also make full shapes with the draw tool. There's a rectangle and a circle, so you're able to just do both.
No one told me that. Okay, hold on. So draw like this one here.
We can't see the. I'd choose the one at the top. I think it's the one that doesn't have anything inside.
Oh, yeah. Nice. And I can do circles too. Circles.
If you hold shift, maybe? They'll be even. I'm not 100% sure on that.
That's okay. That's good. So that's one. And then let's draw the other. Oh, no, I don't want that. Let's draw the other like from here. Wow. Seriously, like my whole life is like a lie up until this point. All right. So we have the E circle and the M circle. So the inside portion are the people who satisfy both M and E. What percent is that going to be?
10%, 0.1.
0.1, right? We've already calculated that, 0.1, right? Now, what's this one going to be here?
0.3.
Excellent, 0.3. Not 0.4, because remember, all of E is 0.4,
Yeah.
but we already have 0.1. That's part of E, correct?
Yes.
So the rest of E is going to be the remaining 0.3. And how about the rest of M? What's that going to be?
0.4.
0.4.
That's going to be the remaining 0.4. And notice, by the way, that when we add them all together, what do we get?
0.8.
Which is what M or E is, which means what number do I have on the outside?
0.2.
0.2. 20% get none, 40% get only M or are only M, 10% are both, and 30% is only E. Does that make sense?
Yes. When doing on the homework or on the quiz, we could do either decimals or
Yeah,
percentages, you said, right?
yeah, I'm okay with either one. I'm okay with either one. So does that make sense?
Yes.
I almost didn't want to clear it because I lose all my text, but I had to. Okay, so that takes us to the end of chapter 4. Now, today is Thursday, and we're supposed to have like a lot of quizzes. And quizzes are good. They keep us on our toes. So we already are going to have a quiz on Tuesday to Thursday on chapter 3. So now that we finished chapter 4, the homework for 4 will be due on Thursday, and we will also have a chapter 4 quiz between Thursday and Tuesday. Is that okay?
Yes.
This section wasn't too hard, was it?
No.
It wasn't bad.
It's fun also. Even.
Okay, so now we do have a few minutes. So let's start chapter 5. I'm only doing this because I remember the last time I taught this course, which is like a couple years ago, or maybe last year. At the end, I wasn't able to finish everything. So if we just say, oh, we're 15 minutes, let's go, we're done. At the end, we'll be kind of behind. So we're gonna take this extra few minutes. Chapter 5, conditional probability and independence. Conditional probability is very important in the theory of probability overall. And by the way, the course so far has really focused mostly on probability and will continue to do so for a couple chapters. And you might be saying, wait, I thought this was statistics. Where's all the statistics stuff? Well, it's coming, but we can't do statistics without probability. So we got to do it first. So group activity. To assess their understanding of probability, a researcher gave the following problem to a group of 4th graders. 10 of the girls in a kingdom are princesses, and 30 are regular girls. Now, I don't want to shame anyone, so I don't think regular girls is really a good term. We're going to call them non-princesses, okay? Because everyone is a princess in their own way, right? Nobody? Okay, whatever.
Yes.
Maybe like other ladies or something.
Other ladies. The other ladies. Right? So all of the princesses are wearing a crown, but so are half of the other ladies. Suppose that you see a girl from a distance. She is wearing a crown. Is it more likely that she is a princess or another lady? That's the question. Now, we're not going to answer it yet, but here are some answers given by the children. Child 1 says, oh, it's a princess because all princesses wear crowns. And number 2 says it's a princess because it's more likely for a princess to be wearing a crown than for a other lady to be wearing a crown. 3 says it's a princess because I really want to see a princess. I'm pretty sure that's not the correct answer. And 4 says it's another lady because the number of ladies, other ladies wearing a crown is larger than the number of princesses wearing crowns. Right? There's 30 other ladies, 10 princesses. All the princesses wear a crown. Half of the other ladies wear crowns. I see a crown. What is it more likely to be? So think about it. Oh, wait, there's a 5th. I missed a 5th. The 5th says, oh, it's got to be another lady because there are more other ladies than there are princesses. So let's see, scroll down. Are there any more? No, that's it. Those 5. So I'm going to throw out number 3. I hope you all agree that your wishes and dreams mean nothing when it comes to mathematics, right? Is it the one on the next page? Well, there's 3 on the next page. So, oh, that's just more coming. No, just those. All right. So I want you to think about it for a second. And then I want you to decide if you think the answer is 1, 2, 3, or 4, or 5. And what I'm going to do after a couple more seconds is I'm going to say go. And I'm just going to want everyone to throw. Oh, I was looking. Whoops. Sorry. I saw a chat and I didn't scroll down. Someone said it's 4. Someone said it's straight up 4. So maybe they're right, maybe they're not. I'm not going to say one way or the other. But when I say go, I want everyone to put whatever number they believe is correct. 1, 2, 4, or 5. Okay, so I'm going to count down from 1,000,000. No, I'm going to count down from 3. 3, 2, 1, go. Type it in. Well, either we got major peer pressure going. Ooh, someone did say 5. Someone said 4,444,444, which, just so you know, is not a valid answer. There's only 1 through 5. But most people said 4. Wait, just kidding. It's 5. Oh, okay. I was also kidding. Oh, no, you went from 4 to 5. I see. So a couple people say 5, and most people say 4s. Nobody said 1 or 2. So let's think about it. Let's write down the information again. So there's 10 princesses, and therefore there are 10 crowns that come from the princesses. There are 30 30 regulars. How many crowns come from the regulars?
15.
15. Now, if I see a crown, then the only people that are even under consideration are these 25, correct? The other 15 regulars don't count. They don't exist for this problem. Because given the condition that a crown is present, I only have to concern myself with these 25 people. Of those 25, what's the probability of being a princess? What's the probability of being a princess?
10 over 40.
Not over 40. I'm not looking at all 40 people.
What is that, 25?
10 over 25, because only the 25 crowns are under consideration. And what's the probability of being a regular person?
15 out of 25.
15 out of 25. So therefore, ultimately, the reason why, what was the question again? The question was, which is it more likely that she's a princess or a regular girl? So it is more likely that she is a regular girl. You can see the probability is higher, which immediately throws out 1 and 2, which is good because no one said those. And let's look at the reasoning behind 4 and 5. 5 says it's a regular girl because there's more regular girls than there are princesses. That's true, but I'm not using that number. I don't care how many regular girls I have. What I care about are how many regular girls are wearing crowns. Those are the only ones that come into consideration. 4 says a regular girl because the number of regular girls wearing crowns is larger than the number of princesses wearing crowns. All that matters are crowns. The other ones are irrelevant, at least for this example. Everyone's special, I know. But for this particular problem, the only ones that matter are the people wearing crowns. So the answer was 4. Does that make sense? Yes, no, maybe so?
Yes.
Yes.
Let me clear this stuff. How do I clear this stuff? Oh, there you go. All right. How might you present the information in a way that would help fourth graders visualize the situation? So here's what I would do. I would make what is called, oh crap, I know, I can do better. I would make it's called a two-way table. I would make what's called a two-way table. I would have better do it here. Okay. So here we have crowns and no crowns. Here we have princesses, and here we have regular ladies. How many princesses are there that are wearing crowns?
10.
10. How many princesses are not wearing crowns?
Was it 0?
0. How many regular people are wearing crowns?
15.
15. How many regular ladies are not wearing crowns?
15.
15. So because I know that I saw a crown, I can ignore this whole row. It's irrelevant for this problem. And the only ones that matter are the first row, where there's more likely to be a regular lady than there is to be a princess, because it occurs 15 times versus 10 times. Does that make sense?
Yeah.
Yes.
Okay. This is the concept of conditional probability, where you're asking for how likely it is something occurred, given okay. I don't know what I said that was so funny, but I do like to think that I'm kind of humorous, so I do appreciate the laughter, but maybe not the best time for it in the middle of this momentous moment where I was going to convey some really important information. So conditional probability is about the likelihood that something occurs given some additional information. In this case, it wasn't about is it more likely to see a princess or a regular lady, but given that I saw a crown, is it more likely to see a princess or a regular lady? And that information, that given that I saw a crown, changes how likely it is that something occurs. This is the idea of conditional probability, which we'll get to next time. So we will stop here. Are there any questions? Going once, going twice. I'm going to stop